The first presenter, Evan, comes from the University of Toronto, and it's a pleasure to welcome him here, participating in the session. Thank you for making the time and effort to come out here.
Thank you for inviting me. Ladies and gentlemen, welcome to our second session about UHPFRC and high-performance materials. I'd like to acknowledge my co-authors, Brittany Yap, who is the master's student who is performing these experiments, my colleague Frank Vecchio, expert in shear at the University of Toronto, and Steve Foster from the University of New South Wales, who was the person who brought us all together to get this work done. Now, we're familiar with ultra-high performance fiber-reinforced concrete, and there have been many kinds of experiments done over many years, of course, to quantify and understand this material, and these must continue. Material level tests, lots of those. Direct tension tests, subject to the challenges of boundary conditions. Flexural tests, both in terms of prisms and large-scale members. Shear tests on large-scale members, answering some basic questions like the fact that there's no coarse aggregate in UHPFRC means we expect a lower shear resistance on a crack. On the other hand, we have a large number of narrow cracks, and the narrow cracks have better shear resistance than wide cracks do, so that could compensate for the first. Of course, there's fibers, which will hold the crack together as well. We potentially have no reinforcement in some directions, and that calls into the question, do we have a size effect? And quite possibly we would, actually. If we're dealing with experiments that are pre-stressed concrete that have a large pre-stressing bulb, we might have a large amount of shear carried in the bulb, and identifying how much shear is carried in the web versus the bulb can be challenging. So the way to solve that problem, in my opinion, is to do a pure shear test. A pure shear test is an experiment where you have no moments applied, only shear applied to the specimen that you're looking at. To do that, you need a special machine. So what we use at the University of Toronto is our shell element tester. We've been using this for about 30 years. It's a large blue frame, as you can see. And the specimen itself, let's see, do I have a pointer here? I do, but okay, right there in the middle, that's the specimen basically, and same thing over here. We consider that specimen to be essentially one finite element, subjected to pure shear. It's about 1.6 meters across, 1.6 meters tall. The specimen's 200 millimeters thick, so it's about half a cubic meter of UHPFRC. Now the way this works is that you start out mentally with a model of what the specimen will look like. Internally, we'll have one layer of reinforcement at the back, and this very first test that we've done here on UHPFRC and shear contains reinforcement in both directions, because we wanted to make sure their anchorage was in good shape, but still has good information otherwise. We have a second layer of reinforcement inside as well. We then cast it solid in UHPFRC, bring it to the testing machine. We have 20 horizontal actuators that will control the forces horizontally, each specified to give the exact same force, but they're servo-controlled, meaning we can actually make sure it's safe to do the operations on it. At the same time, we have 20 vertical actuators that are pushing down vertically. This means the central area is in tension horizontally, compression vertically, which we'll see in a second to shear if you use a Moore circle. Also, we have an additional 20 out-of-plane actuators to hold it in place to make sure that it stays stable, because otherwise we could have a stability problem. This also allows us to do tests on out-of-plane bending, etc., but we're dealing with in-plane pure shear at this stage. What we're looking for here is something like this, where we have reinforcement in one and another direction, with shear forces around the outside edge. From a Moore circle, we can see that if we chop that down, that's the same thing as having compression in one direction, tension in the other, to which we then rotate and put it into the machine to allow us to actually do the testing the way we do it. So the reinforcement is at an angle, which means that the horizontal forces, vertical and horizontal, provide shear internally. And we found that with regular concrete, this works quite well, very consistent between beam shear tests and the experiments done here as well. It's a measurement basically of what the web is doing without any other components around the outside edge, which is important to understanding the material. Here's a specimen that we tested. As I said, 1.6 meters each direction. You'll see that there's plenty of additional reinforcement near the ends to ensure that we can have this is not bright enough. Do I have a mouse? I do not have a mouse. Okay. I'll try to use a pointer. Unlike normal specimens we've done in the shell tester, of course, this material has a significant post-cracking tensile strength, and as a result, the anchorage needs to be significantly more complex. I was nervous, frankly, that this reinforcement at the edge with all the additional bars would make a challenge for casting. I was wrong. The material flowed very well and had no trouble getting around the bars, and so our anchorage worked quite well. The way that tension gets into the specimen is that we have blocks with bolt holes in them so that the actuators apply to the bolt holes, go into the steel, and then get distributed into the concrete itself. The test region is sort of the central 2/3, and indeed that's where it failed as well. Here we are with our friends at FACA Construction from Dura Concrete Canada in Windsor, Ontario, casting the first specimen. That's Brittany on the left-hand side. You get a sense of the scale of the specimen. Here we are putting the concrete onto the specimen as well. You can see it. The reinforcement is acting as a net that's stopping it, but the concrete is quite happily going around that. I was pleased to see how well it flowed. This is a zoomed-in view of the fibers, basically giving us some issues of fiber alignment issues around the reinforcement. But in the end, after the failure, we did not see any evidence that the fibers at the crack had any non-randomness. So they appeared to be random and in good shape, and the casting went quite well. The material behavior as we observed it, as I said, we had about 500 liters of the material. We had 2% fibers, 1% were 20 millimeter straight fibers, 1% of 20 millimeter hooked fibers. The compressive strength ultimately was about 171 MPa after steam curing, and that was the same number at 14 days as it was when we did the test at 50 days. The uniaxial stiffness from a compression testing was 49.3 GPa. Because of this experiment and we're doing compression in one direction, tension in the other, it means that the stiffnesses we measure are biaxial values, and as a result we can get Poisson's ratio out of it, and we got a value of 0.19. It's nice to see linear elastic principles work before things crack. It's all in good shape. You can see the results from the modulus tests, the flexural prism tests, and you can see, as usual, there's some variation in that, but overall good behavior, significant strain hardening behavior. Now, to operate this machine requires a significant team, and the specimen is up on the top, and during loading, no one's allowed to go near it, and therefore we have a television so we can watch it, basically. And we have our displays down below. I think we're violating rules of ergonomics in the number of graphs we're showing simultaneously here. But we've learned that when you have 60 actuators with 60 displacement channels coming back, you need to be able to see what's happening and move your eyes around in a hurry. So when new students arrive, they see this and they are very panicky because they say, this is far too complex, what are you doing? But with practice, we're able to get the information. And most importantly, I want to draw your attention to the bottom of the screen. Despite all the fancy computers, we still use a piece of paper with a checklist to make sure that we actually have checked everything and we're all in good shape, because this machine is strong enough to break itself. And so therefore, it's definitely strong enough to break us. No one has been hurt in this machine in the last 30 years, so we're in good shape though. So we began loading the specimen. After cracking, we were, unusual for me, I'm new to UHPFRC. I'm more of a regular concrete person, so to speak. And the fibers totally changed the behavior from my expectations. We had not a contiguous crack going across at all after cracking had occurred. So significant numbers of small cracks. Those numbers are widths in millimeters. This is about halfway up to failure, so service loads in effect. 0.05, 0.1 millimeter cracks. And because they're not contiguous, they can't fail in shear. It's only when we actually have a kinematic mechanism where a single crack can slide along it that that'll occur. And that's, of course, one of the reasons the material works so well. As the load got higher, eventually those cracks got wider. If you have sharp eyes, you can see some of the cracks are now at 0.15 millimeters wide. And more importantly, there's one big crack near the bottom that has actually become a problem. We can see down here near the bottom. Because of the way the machine works, we can only have cracks at the outer faces between the steel plates. And so there's some concentration of crack width there, and that started an unzipping process. At this point, you can see, though, it's cracked on the right-hand side, but not on the left. That's unusual. That's the fibers allowing that. That's not something normal concrete does. We'll see that did cause some interesting results from the instrumentation on the surface. But as the load went up further, the crack got wider until it opened up to about 20 millimeters, at which point we stopped the test. Very large shear strains, very good performance. This is a look into the crack at failure. If we look in the back, we can see that there is a conventional reinforcing bar right there off in the distance. And we can see, of course, the fibers after quite happily having pulled out. And that was ultimately how the member failed, pull out of the fibers. And we kept unloading until we weren't eager to actually have rupture of the bar, so we stopped the test before it got to that stage. Here's the behavior in terms of the shear stress versus shear strain. So initially it was linear elastic. You see we did an unloading cycle there and then proceeded to load up after cracking as progressive cracks got wider and more cracks formed. We were very surprised to see how linear it is after cracking. Normally we would expect to see nonlinearity in there somewhere. Instead, we did all this work to measure two slopes, but we're very excited because modeling two slopes is easy. And so surprisingly linear. Also, if you note carefully, each one of these unloading cycles where we took the photographs, we had to unload to make sure it was safe. Of course, almost no creep actually during the unloading cycles. But if you look carefully, you'll see that the slope of these unloading segments keeps on going down as we go up. That's because as new cracks form, we end up with more elastic behavior coming from the fibers and less from the concrete. And so there's a transition as things get softer. Ultimately, up at 10 megapascals of shear, one of the cracks got too wide, as we saw, and it opened up. The unloading curve down here happened over about 10 seconds, so it was under control the whole way. And that was basically pull out of the individual fibers. So that specimen had failed, but we said, let's keep on going to see what happens. And we ended up having a very long yield plateau, I don't know what to call it, basically going out for a long distance afterwards. The strength of the reinforcement inside was about 4 megapascals by a plasticity model. So even out here at 1% of shear strain, which is enormous, we had 6 megapascals being resisted, 4 of which could have come from the internal steel. So the fibers somehow kept on working, actually, even after we had very wide cracks forming. So that indicated significant ductility in the response. And then finally we unloaded, because we were now getting worried that the displacements were too large. Once we have these results, we're now able to look at the principal directions, principal compression direction, principal tension direction. The strain showed us that it wasn't perfectly horizontal and vertical. There was some twisting of a few degrees, but that's not important. We're able then to calculate what we have as the principal compression behavior and the principal tension behavior. Now, the principal compression behavior is the compression stress versus the compressive strain. Don't worry about the wiggle on top. We'll talk about that in a second. The initial stiffness was what we expected to be from linear elastic behavior. After the cracks formed, there was a significant decrease in the compression stiffness, such that by the peak load, it had a secant stiffness of only about 2/3 of the uncracked response. That indicates that even though the compression stresses were going between the cracks, they were still feeling the effects of the cracks. But unlike regular concrete, where the curve will basically curve over, it went back to being stiff again and proceeded to go back up linearly again up to the peak. The curve in the top, which of course, if you know your energy principles, is physically impossible, what that actually indicates is that we had a crack that was partial width to the specimen and not the other half of the specimen, which meant that the instrumentation on the surface, which on our calculations assumes uniform strain field, it was not a uniform strain field. But once that we kept on pulling, that went away. We ended up with basically a plastic behavior going out until we ultimately unloaded. No sign of crushing of the concrete. We probably can't crush this concrete with our machine. It's not strong enough. In the tension direction, once the steel was subtracted, we have, for comparison, a conventional concrete with the same cracking strength down there in light blue. And on top, we measured the behavior of the hardening behavior of this material, and ultimately the pullout on it as well, going further down to the result. So these results allow us now to develop numerical models to try and understand this behavior and what the next steps are on that front. We had 4 more tests after that one, 2 of which have been performed so far. The second one had reinforcement in only one direction, and in that experiment, which was recently completed, so I can't show you yet, that meant that there will be a shear demand on the crack. That did not seem to change the behavior, which is good. The third experiment, we're trying to understand exactly what it meant and how it behaved, so I'm not going to tell you about that one either. And the next 2 have yet to be cast. We're going to do further analysis of the tests and develop a numerical model. What we can see here is the last point here on the graph on the right is from the computer screen in our displays. The dashed line you can see barely if you look closely. That was the prediction before the experiment. We like to do predictions of the behavior before we do the test and then draw the plotter line on top of that. What we learned from this is that the variable engagement model from C. Foster was actually conservative, but pretty good. What it showed, though, is there should have been some sort of a plateau before we ended up having post-cracking behavior, and that's not what we saw. We went right to the post-cracking behavior, which is good, and we can see that we have an opportunity to improve things. I'd like to thank the Australian Research Council for paying for this, and Dura Concrete Canada and FACA for helping us with the construction. Thank you very much.